So let me take over from Ludwig as he comes back online. Maximilien Debias is a professor at the University of Environmental and Occupational Health of the School of Public Health at l'Université de Montréal. Professor Debias is responsible, with Professor Lavoué, of the occupational hygiene option of the master's degree in environmental and occupational health. He is the scientific co-editor of the journal Travail et Santé. Its research activities aim to evaluate and control occupational exposures to various contaminants, including nanometric particles. So it's my pleasure to invite Maximilien to share with us his talk, Best Practices Guidance for Nanomaterial Risk Management in the Workplace. Maximilien. I'll invite Ludwig to present our second speaker.
So first, sorry, I didn't know what's happened with my connection, always at the bad time. And thank you, Marie, for introducing Maximilien. So let's continue with our second speaker, Stéphane Allais. Stéphane Allais is a professor in mechanical engineering at l'École de Technologie Supérieure, where he has been a faculty member since 2003. During his career, Professor Allais participated in 15 research projects related to aerosol. These projects focus on two main things. The first one, computational fluid dynamics simulations of the aerodynamic behavior of airborne particles and the effectiveness of local and general ventilation to mitigate the exposure in workplace environment, as bronchoscopy unit, anatopraxy room, etc. And the second one, the effectiveness of personal protective equipment against aerosol. Current research emphasizes the filtration efficiency of washable barrier mask and the development of a predictive collection efficiency model of non-woven fabrics used for manufacturing protective clothing. So it's my pleasure to invite Stéphane to speak about risk assessment of occupational exposure to airborne nanomaterials using numerical simulation. Stéphane, you have 20 minutes for your presentation.
Thank you very much, Ludwig. I'll start with share my screen. Can everyone see my presentation?
Yes.
Yes, no, okay. Just to reduce this. Okay, good afternoon, everyone. Good morning or good evening, depending on your location. The objective of my presentation is not to present all model in detail, but only to explore the possibility offered by some exposure model. So sorry, here we go. Among the four possible routes of entry of hazardous nanomaterial, which are inhalation, ingestion, high and dermal absorption, inhalation is considered as the most significant pathway by which an employee is exposed to nanoparticle. You know, in a typical 8-hour shift, the lung exchange approximately 3,000 liters of air. This volume can be much higher if the employee perform heavy labor. So if we want to provide a quantitative estimate of occupational exposure to airborne nanomaterial, there's basically two options. First option, the concentration will be are measured directly, experimentally. And the other option, the concentration are estimated by mathematical relationship in form of model. In the presentation, I will not make any distinction between materials that are prepared deliberately at the nanoscale and ultrafine particle, natural origin or not. So why do exposure modeling? Of course, to evaluate the risk of exposure, but also the measurement of airborne nanomaterial can be challenging. It's not possible to monitor every situation everywhere. There are some limitations associated with the device. Also, there's a multitude of scenarios. Source emission, number of particles emitted per minute, particle diameter, size distribution, the airflow in indoor environment change from one room to another, different room layout, air change per hour, presence of local exhaust system or not. It takes some time also to collect the data and the fee associated with the measurement. So mathematical modeling can help the occupational hygienist to understand the influence of key parameter and support the decision process. And from an engineering point of view, modeling can contribute to the development of efficient ventilation system and to assist the hygienist to recommend mitigation measure. However, the aerosol physico-chemical properties at the receptor, at the worker, can differ significantly from the properties at the source of emission. And this figure summarizes the principal mechanism affecting the concentration, morphology, size distribution of nanomaterial between a source and the receptor. These mechanisms affect the aerodynamic behavior and hence the degree of actual exposure. So the transport of airborne nanoscale particle through the air is governed by the aerosol general dynamic equation, or GDE. This equation describes the particle dynamic under the effect of different physical chemical process. For example, the advection, the transport of particle by the air movement, the diffusion, Brownian diffusion, turbulent diffusion, coagulation process, where two particles collide to form a new particle, larger, surface growth, nucleation, other forces such as gravity, temperature gradient, electrical potential gradient, etc. Solving this aerodynamic equation is very complicated with the direct numerical method. It's also time-consuming and not very practical for a real exposure scenario, but several approximate methods have been developed in form of model. So a model provides a mean for representing a complicated system into an understandable way. All models are based on assumption, and they are basically structured like this. We have a set of input data that feed the model. The exposure model can be very simple, a simple algebraic equation, or a set of complex differential equation, it depends. And at the output, the numerical result, it can be, for example, the slice mass fraction of an aerosol inside a space, isosurface of velocity, or a specific concentration in the room with respect to times. Models vary greatly in complexity, and one should know what a specific model can do, what it cannot do, and what are the assumptions behind the model. So in the presentation, I'll present three models, but they all neglect the coagulation process. Coagulation can also be very complicated. The equation describing the kinetic of coagulation is nonlinear. It depends also on the particle size distribution, the flow regime, free molecular or continuum regime, and the turbulence inside the flow also affect this process. It's doable, and some approximate methods have been developed. And given the time scale typically encountered in workplace, coagulation should be considered as the most important mechanism affecting the aerosol particle size distribution, not the dispersion, but the size distribution. And the rapidity of this process is directly related to the number concentration inside the space. The higher the concentration, the faster the coagulation process. But this time here must be put in relationship with the time constant created by the ventilation system. For example, if we take a lab, 300 cubic meter, and the ventilation system is based on the dilution principle, so completely mixed, the time constant will be reduced if we increase the air change per hour inside the room. The time constant represents the average time spent by air molecule inside the room. So if we increase the ventilation, the time constant will be reduced. And this time constant should be compared to the time scale for the coagulation process in order to decide if we should consider coagulation or not for a given exposure scenario or given simulation. So first type of model, they are called CFD model. What is CFD? It's computational fluid dynamics, simulation of fluid system using a mathematical problem formulation in form of a set of differential equation and numerical method to solve these equations, spatial temporal discretization, solver, numerical parameter, etc. And the CFD model solve the conservation law that govern the time-space evolution of air field within a space, pressure field, temperature, concentration, etc. And then in the model that I will present, I neglect, as I said before, the coagulation. Eulerian approach has been adopted. That's mean all particles are not tracked individually. one-way coupling. What I mean by that, it's the flow field influence the dispersion of particle, but the particle does not influence the flow field. And the main objective of this simulation is to determine the concentration of airborne nanomaterial in the computational domain with respect to time. So for indoor application, the aerosol transport is largely dominated by the fluid movement. So before attempting to model the aerosol transport, it's very important to carefully model the air movement. And the air movement, they are inside spaces. They are generally, they are three-dimensional, generally unsteady, turbulent. There's basically two approaches to solve these governing equation: Reynolds average Navier-Stokes equation or largely simulation model. And if for a given situation, we have significant temperature gradient, thermal source or sink, the equation of energy should be added to the model. And also we have a mass transport equation for the particle. Z is the mass of particle in cubic meter divided by the total mass in 1 cubic meter. And this mass fraction is related to the number of concentrations, the aerodynamic diameter, and the particle density. And the equation for this mass transport is a well-known equation. It's widely used for gaseous contaminant with one exception. We added a term here, U depth, deposition velocity, that can be considered in the model to consider the deposition of particle by gravity, temperature gradient, and diffusion. So one example of the application of this model, it was a project for nanoparticle transport in an animal exposure chamber. The main objective was to investigate in a rat model the pulmonary toxicity induced by titanium dioxide nanoaerosol, ANATAS in that case. So several groups of rats were exposed to TiO2 for 6 hours. And for the CFD simulation, the objective was to change the position of the deflector, like you can see here, and the amount of air at inlet 1, fresh air, and also the air and aerosol at inlet 2, in order to create a well-mixed condition in the exposure region right here. The rat, they are put in plexiglass tube 1 up to tube 7. The mathematical model rely on the Reynolds average Navier-Stokes equation. We did not consider in this model the settling of particle because the diameter is pretty small, around 30 nanometer. Turbulence model is K omega model, and the mass transport for the nanoparticle. We can see here the spatial discretization and the experimental setup here. So some result, as I said, the objective was to investigate the flow distribution. This is an illustration qualitatively, the velocity streamline. The velocity streamline inside the exposure chamber, isovelocity contour, two-dimensional mass fraction, in order to be sure there's a good mixing between the fresh air and the nanoparticle. We also compared the numerical mass concentration to the experimental one in the rat breeding zone right here. That's what the nose of the rat is located. So the agreement is excellent, giving the assumption of the model a 7% difference between experimental and numerical is considered to me as excellent. And if I come back to this slide, also we check the concentration at the tips of plexiglass tube 1, 2, 3, up to 7, just to be sure that the concentration is uniform. And in fact, the difference in concentration between all the plexiglass tube was below 3%, which is again very good. Another example, application of CFD model is the exposure assessment of airborne contaminant in a thanatopraxy room. 3 different rooms, a small size room, 67 cubic meter, medium size and large size room at more than 700 cubic meter in volume. In this project, we investigate the exposure to personnel in function of particle diameter, 2 micron, 5 micron. I know it's not in the nanoscale, but the CFD model is very similar than the model presented in the slide before, except we added the deposition by gravitational settling inside the model, and the numerical technique, it's not the same. It's a largity simulation code. So we investigate the effect of particle diameter in the concentration, 2 and 5 micron, source location, the effect of air change per hour, and also the ventilation strategy. For example, if I take this room here, the medium size, we have 4 wall supply grill, S1 to S4, and a ceiling diffuser, square ceiling diffuser, S5. If we keep the air change per hour fixed, but we change the ratio of the air supplied by the ceiling diffuser compared to the wall grill, we were able to show a difference in the exposure plus or less 30%, which is significant according to the ventilation strategy. So all of this while keeping the air change fixed. So some example result, qualitative dispersion of the particle inside the space. Simulation is short because the file becomes large very quickly. On the right side, we can see here the surface deposition by gravitational settling. There were no significant temperature gradient in the room under investigation. This is the medium size. The mass fraction in the breathing zone at a specific time, but we can also integrate this mass fraction to have average value. So the red zone represent high concentration, and the blue region almost zero particle concentration. The mean concentration inside the room with respect to time for air change per hour, CAH is the same thing that air change per hour, 1 for 10.26, the experimental value, and up to 12. And also the fate of particle. When the particles are ejected in the environment, there's 3 possibilities. They remain airborne, they are extracted by the system, ventilation system, or they settle down on the solid surface. So that's, we can see here, the emission scenario in Nanotechnology lasted 1.5 minutes. And after that, we follow the fate of particle. Initially, most particles are airborne, 90%. The extraction dropped rapidly, goes almost to 0 after 30 minutes. The fraction extracted by the ventilation system is initially, after 90 seconds, 10%, and raised almost to 100% at the end of the simulation. And the deposited fraction remains pretty small. It's 2 micrometer particle in that case. It's below 0.7%, so small in that case. It's not illustrated here, but by CFD, we can also determine the mean age of air in many locations inside the space to identify recirculation region. Also, if the room is maintained in negative or differential pressure, we can couple the CFD with an infiltration and exfiltration model. CFD is useful, but there are some drawback to CFD model. It requires know-how. You need also an accurate space discretization. Simulation can be computationally expensive. Now I'm running simulation for a swimming pool, exposure to a gaseous contaminant. And a typical simulation on a 12-core processor takes about a week to obtain the results. So it's a long time. There's also always some uncertainty in the input of the model. And there's not many open CFD code available to the public, and the commercial code are generally expensive. So that's why I present another type of model, simpler one. They are called 2-zone model. The idea behind this model is pretty simple. The zone is divided in a far field region, a near field region near the source, in a far field region, the remainder of the room. And we have only 2 values in this model, a near field concentration with respect to times, just 1 value, and 1 far field concentration also with respect to time in the pink region. So this model are based on a mass balance equation applied for each zone. For example, in the near field, the nanoparticle or the particle concentration in the green region is directly related to the intensity of the source. The source is located here. The movement of particle from the near field to the the far field, sorry. So it's a loss of particle. the particle in the far field that move into the near field, and the loss of particle minus sign for the deposition on solid surface. For the far field, we have basically the same equation, except the source term is not there. And we also had ventilation for the extraction of particle inside the space. So these two-zone models are useful. For example, if we have a particle size distribution at the source, it's possible to separate this size distribution into, for example, 3 or 4 bin of particle size and apply these mass balance equation for each bin independently. Other type of model, simpler, single mass, single zone model, also called well mixed model. In that case, we just have one concentration for the whole space, also based on a mass balance equation. Here I added the ventilation system. It's possible also to do that with a 2-zone or CFD model. We can include in this model the effect of filtration inside the duct, ventilation duct. We have the inlet source, the extraction by the ventilation at the outlet, and a deposition module to take into account the settle of particle, usually by gravity. These models are very simple, and one-zone models such as the Quantam software developed by the NIST, they can be used to predict the contaminant transport in a section of a building and even the whole building, which is very difficult, almost impossible to do with CFD code. Right now, I supervise a master's student with Professor Vench to investigate this well-mixed model experimentally and by numerical simulation. In fact, we would like to determine when the deposition should be considered according to the particle diameter, the source, the air change per hour, and the particle density. There's only few software available for the public in general to determine the exposure to airborne nanoparticle. One of these tools is the Engineering Nanoparticle Airborne Exposure Tool developed by the National Institute of Standard Technology. This tool is available freely on the internet, and also the nanoparticle coagulation tool, where also free. The user must provide a file that specific the air properties, the initial log normal distribution of particle, the number of bin for the simulation, room data, floor surface area. This is my last, just another slice. And again, these tools are available on the internet, the Quantam software, as I said before, and the EH mode software. It's an Excel file, free, with a set of macro. EH mode, it's not for particle, it's for gaseous contaminant only, but it can be very useful in a situation where the particles are small. I would say maybe 1 micron or less. If the concentration is low, to neglect the coagulation process, EH mode software can give you an idea of the exposure in function of the air change per hour, room volume, intensity of the source, constant emission, sudden release of particle, or for starting from an initial concentration, how much time it takes to flush the particle from a given space. So it's a useful tool, even it's for a gaseous contaminant. Thank you. Just stop the sharing. Here we go.
Merci beaucoup, Stéphane. Thank you. Okay, so we have some questions for you from Yizang. Thanks for the interesting talk on the modeling. I have a question on metric unit. Seems that all these models' outputs are in traditional mass unit. Is there a way to convert the mass-based to number-based or surface-based unit, which may be more relevant to inhalation exposure to nanomaterials?
Yes, as I presented before, we can relate the mass concentration to the aerodynamic behavior, aerodynamic diameter, and the number of particles. Since the objective of this code is to modelize, CFD code modelize the aerodynamic behavior, we use as a metric the aerodynamic diameter inside the CFD code. But with the Z parameter that I presented before, which is the mass of particle divided by the total mass, particle and air in a 1 cubic meter, we can convert this mass concentration to a number of particles. But to do that, we need a particle diameter. We don't have any choice. We have to fix the diameter. Yes, it's possible.
Merci. Second question is from Ali-Reza Falafar. Thank you very much, Professor Ali, for the presented mathematical models. I think it was very well aligned with Professor Debia's presentation to use the model when it's not possible to direct measurements. My question is that in terms of using a simple model as a two-zone model, how can we separate the zones from the near field and the far field? And according to your experience, what will be the criteria?
It's a very good question. And in fact, there's no consensus of the size of this near field. Maybe that's the problem with the two-zone model. Some researchers said the near field should include only the vicinity of the source. And other researchers said the near field should also include the worker, the reading zone of the worker. It depends. Usually we say that the near field should be around, if we take, for example, a cylinder, maybe 1.5 meter in diameter and maybe 50 centimeter height. But it changes. It depends also the source of nanoparticle. Is it a point source or an emission by a large surface or a leak from a device? It depends. So it's by experience, you decided what type of near field, and also you have to interpret the result because the size of this near field will affect directly the prediction and the concentration. So unfortunately, I don't have a specific answer. It's a case by case decision, and also some experience.
Merci. And a question from Professor Brady. Are the model considering different sticking factors of nanoparticles on various surfaces in a room, especially if some are colder or more textured, for example? And in any ways, would that be a good strategy for captation?
For captation, I don't think if we have a cold surface, nanoparticle will tend to stick to this cold surface, and it's the opposite for the hot surface. That's what we call the thermophoresis. It's possible to consider that aspect in numerical model. There's a CFD code called Fire Dynamics Simulator FDS. It's freely available on the web. This code considers the setting of particle by diffusion, thermophoresis, and also inertial impaction. So yes, it's possible. Is this factor significant? It depends, again, of the temperature gradient that we have and what is the importance on other physical phenomena. And for the deposition on surface, the roughness influence, yes, it influences the deposition rate. There are some models that consider the roughness of a surface. But is it a good captation? I would say no. If you want to reduce the concentration, the simplest way is to use ventilation and local captation filtration system. Deposition, especially for small particle in general, is not very high. When we have larger particle, 50, 100, and 500 micron, it becomes significant. But below 1 micron, deposition is not very high. It exists. It's not zero, but it remains small. In the bronchoscopy, not bronchoscopy, but thanatopraxy result that I presented before, 2 micron, 30 minutes, less than 0.7%. So it's not very important.
So coming to that example of the thanatopraxy, say in a mortuary environment, you could have very different sources, right? You could have volatile organic compounds, drugs, or whatever. And so how do you extract some best practices from these types of workplaces?
What do you mean by best? The
Well, in
recommendation?
terms of protection for people who work in those environments.
They have to wear facial protection, but in the project we investigate more the role of engineering control measure, so the ventilation. If we have formaldehyde, they use formaldehyde for the tantopraxy. It's possible to include many contaminants in the CFD code, but don't forget, if we add, for example, 5 contaminants and you would like to follow the space dispersion of this contaminant, you need 1 equation per contaminant. Okay. So the model becomes big. It takes longer time of simulation, but it's possible. Even as the coagulation process, it's possible to modelize, but there's a cost for that. It's a longer simulation time, but it's possible, it's doable. Okay.
Thank you very much. Ludwig has a question. Ludwig?
Oh, I'm afraid, Ludwig. A big question, difficult one.
No, thank you very much. A very short question. In your different model, you consider a punctual source of particles, but is it possible to take in account the resuspension of the particles due, for example, of the
thermal
movement
rebound?
of the, sorry?
Like the thermal rebound?
Not the thermal rebound, the movement of the worker in the place. So is it possible to modelize this resuspension of the particles? Yes,
I reviewed a paper recently for the journal Building Environment, and they consider that aspect. When people walk on a rug inside a space, they can, the particle that were on the surface can be put in suspension. And they use an empirical model to consider that aspect. And they said it's significant for larger particle. In the paper they investigate, I don't remember exactly, it's for particle 50 micrometer and more. They said for a smaller particle, I don't remember, I think it less than 10 micrometer, it was not significant. But it's an empirical relationship they use in this paper. It's possible to do that, yes.
Okay, thank you.
The mechanical suspension of particle, yeah, it's possible.
Thank you.
Merci beaucoup, Stéphane. Thank you very much for this very interesting talk. And now I'll invite Ludwig to present our last speaker.
Just stop the sharing of my screen.
So I'm pleased to introduce our last keynote of the day, Loïc Wingert. Loïc holds a bachelor's degree in physics and chemistry from the University of Joseph Fourier in Grenoble, in France. He also holds a professional master degrees in chemical engineering with a specialization environment on chemical processes and effluent treatment, solid, liquid, and gaseous. He then obtained a PhD from the University of Lorraine, France, from the French Institute of Occupational Health and Safety, and from the Reaction and Process Engineering Laboratory of the National Center of Scientific Research. Following this PhD obtained in 2017 on the separation of ultrafine metallic particles by granular beds, he continued his career with a postdoctoral fellowship on protective clothing with, against solid aerosols at the École de Technologie Supérieure in Montreal and at the Institut de Recherche Robert Sauvé en Santé et en Sécurité du Travail, Rsst, in Montreal. Since 2018, as a scientific professional at the IRSST, specializing in aerosols and their filtration, he has been participating in and conducting research activities to study workers' exposure to aerosols, nanometric and micronic, and bioaerosols, but also to evaluate the performance of certain protective equipment. Finally, he works on the metrology and the characterization of aerosols applied to occupational health and safety, such as those of ultrafine particles emitted by certain processes. So it's my pleasure to introduce Loïc Wingert to speak to us about impact of airborne nanomaterial characterization on risk assessment and protection. Loïc, you have 20 minutes for your presentation.
Thank you, Ludwig. presentation. So, can you see the presentation?
Yes.
Correct.
Good.
Okay. Okay. Good afternoon. So, thank you, Ludwig, for the introduction. Today, I will present you a brief talk about the impact of airborne nanomaterial characterization on risk assessment and protection. Sorry, okay. So let's have a few words about the IRSST, the institute where I work. So the Institut de recherche Robert Sauvé en santé et en sécurité du travail. It's an institute for occupational health and safety in the province of Quebec. It was established in 1980, and so it's one of the oldest OHS institutes in Canada. The RSST mission is to contribute through research to the prevention of industrial accident and occupational disease, and to the rehabilitation of affected workers. We also have to disseminate knowledge and serve as a scientific reference center and expert. And finally, we provide the laboratory services and expertise required to support the public occupational health and safety network. Now, what's the relationship between the IRSST and the Nanoworld? Here you will see a big picture of the Nanoworld. I won't give too much details. You have here detail about the dimension of the criteria for particles or components to belong to some of the nanomaterial category. The largest category are the nanomaterials. The nanomaterials are divided into nano object and nanostructure materials, and we find inside of the nano object nanoparticles, nanofiber, nanosheets, and inside of the nanostructure materials, aggregates and agglomerates, nanocomposites, and nanoporous materials. At the IRSST, we are mainly interested in particulate nanomaterial, PNM for the rest of the presentation, and we are mainly interested in their aerosolized form, and sometimes also interested in the manipulation of powder of PNM. So we mainly work with nanoparticles, nanofiber, and aggregates and agglomerates. So how does the IRSST deals with OHS PNM aerosol issue? Through three main research aspects. The tools, the first one are the tools for evaluating and preventing workers' PNM aerosol exposure. The second one, the prevention, exposure assessment, and toxicology. And finally, protection and mitigation. For all these aspects, one of the key parameters, but not the only one, is the effective density. Before speaking about effective density, I want to give you some definition useful for the rest of the talk. So the electrical mobility diameter, it's the diameter of a singly charged sphere, which has the same electrical mobility as the particle in question. The aerodynamic diameter, the diameter of a sphere of unit density, which settles in still air at the same velocity as the particle in question. To measure particle size distribution as a function of electrical mobility diameter, we can use SMPS, so scanning mobility particle sizer, between 10 nanometer and 1 micron. And for the number particle size distribution as a function of aerodynamic diameter, we can use the APS, an aerodynamic particle sizer between 500 nanometers and 20 microns. So let's go back to the effective density. The effective density is the density that must be applied to the equivalent sphere in electrical mobility to have the same mass as the real particle of interest. In ideal cases, the particles are spherical, composed of a single material, and are non-porous. In these ideal cases, the effective density is the same as the raw material density. But in real life and in most OHS cases, the particles are non-spherical. They can be agglomerated, can be composed with several materials, and can be porous or non-porous. And in these cases, the effective density is different of the raw material, or can be different from the raw material. And also, it can be size dependent. For an example, here you can see the effective density as a function of the electrical mobility diameter for a graphite aerosol. Graphite aerosol, an example could be soot. So it is composed of agglomerated particles. So you see there is a decreasing relationship between the effective density and the electrical mobility diameter following a power law. So what can we mainly do knowing the effective density? We can convert the electrical mobility diameter into aerodynamic diameter thanks to the effective density. And we can convert the number particle size distribution of PNM into mass PNM size distribution. So let's see some example of the effective density impact. Firstly, for the tools for evaluating and preventing workers' PNM aerosol exposure, the PNM aerosol characterization is important from a metrology standpoint to improve direct reading instrument response. A good example of this kind of instrument is the electrical low pressure impactor called LP+. A few words about this device. It's three devices in one. It's a classical cascade impactor with 14 channels between 10 nanometers and 10 micrometers. So it allows you to sample, to collect particles on substrate for further chemical or gravimetric analysis. But LP+ has also a charger to put the aerosol in a defined and well-known stage charge. And all the stages are connected to one electrometer. And so the LP+ can measure the current induced by the particle flowing through each of the 14 channels or each of the 14 impactors. Thus, the LP+ can measure a current distribution as a function of the aerodynamic diameter. But it's three devices in one because by calculation, it can give mass particle size distribution by converting current into mass, and number particle size distribution by converting current into number. But to do that, in the calculation, the LP+ has to use the charge law of the charger of the LP. And this charge law is a function of the electrical mobility diameter. So you have to, or the LP+ have to convert aerodynamic diameter into mobility diameter to be able to give the right number particle size distribution and number total concentration. And so you have to know the effective density to use this formula to convert one diameter into another. In the workplaces, very often you have no idea about the aerosol's effective density. So for a past project in e-waste recycling factory, we developed a simple method to get a single, so average, but instantaneous effective density value that can be used to be able to use the real-time number particle size distribution feature of the LP+. To do so, we use a coupling to measure simultaneously and in real time the total number concentration with the reference devices, so a condensation particle counter, and by using simultaneously the LP+, as the LP+, being able to calculate only the number particle size distribution and the total number concentration. And after that, at the end of the day, during the post-treatment, for example, when you have one work day of data with almost 500 samples, if you choose samples of 1 minute, you can fit for each sample the effective density so that the concentration of the reference device, the CPC, the number total concentration of the CPC, is the same as the calculated total concentration, number total concentration of the LP+. So this simple method works well. Here you have two graphs permitting to validate this method with the LP+ compared to the nano SMPS measurement, the nano SMPS being used as a reference. So you see here a pretty good agreement between the number concentration, but also in terms of shape of the particle size distribution. You could say that it's not a perfect agreement, and you are right, but just to know what happens if you don't do any fit or anything to know your effective density, here are a comparison with the nano SMPS of the LP+ data with the fit density and with the density of 1. And as you can see, you can have more than 100% of error at the peak concentration of the distribution. So this simple method and knowing the effective density, or at least average effective density, in this case, can really improve the quality of your data, and so your analysis of the exposure, for example. Another example of effective density impact, still in tools for evaluating and preventing workers' PNM aerosol exposure, and still about metrology and PM aerosol characterization. Indeed, the PNM aerosol characterization and the knowledge of the effective density can improve your exposure assessment and your analysis. Indeed, most commonly used instruments for real-time PNM aerosol number size distribution measurement are electrical mobility-based. The better example is the SMPS. And knowing the effective density allows you to convert the number particle size distribution into mass particle size distribution and to calculate the PNM mass concentration. And that could be necessary to compare with the existing threshold limit value, which are still expressed as mass concentration. In addition, knowing the effective density allows you to convert the mobility diameter to aerodynamic diameter, as I said, but this time it could be necessary if you want to quantify the fraction deposited in lung areas. The better explanation is that slide, because for one electrical mobility diameter, you can have several aerodynamic diameter, depending on the effective density. In this table, you have an example of a particle of three particles with the same electrical mobility diameter, but different effective density between 3 and 0.2. And as you can see, the aerodynamic diameter could be really different depending on the effective density between here 123 and 11 nanometers. And if you use this kind of graph to find the alveolar deposited fraction, for example, you will have to use the aerodynamic diameter. And you can see in the last column of this table that it will drastically change the alveolar deposited fraction. You have 40% of deposited particle in the alveolar area for effective density of 3, and 50% for an effective density of 0.2. So you see the major impact of effective density on your analysis and exposure assessment. And finally, still for tools for evaluating worker exposure, as Stéphane said, we used combined strategy, numerical and experimental, to predict, extrapolate the behavior of aerosol in workplace. And as he said, you need the aerodynamic diameter as entry data for your CFD code. And so if your measurement in the real life are done with mobility spectrometer, again, you will have to convert into aerodynamic diameter, and again, you have to know the effective density. Finally, last example, but for protection and mitigation. So as you noticed in the past year, we tested a lot of personal protective equipment or collective protective equipment or mutual protective equipment. I don't give too much detail about that, but here you have some example of each type of protective equipment. But for all this equipment, we often have to measure the fractional collection efficiency for a wide range of particle size between 20 nanometers and about 2000 nanometers. And to cover the whole size range, we use a coupling of SMPS, so with the mobility diameter, and APS, measuring the aerodynamic diameter. Also, salt aerosols are often used because they are non-hazardous, less expensive, and we can perform with this type of aerosol more rapid measurement compared to PSL sphere, for example. Most commonly used salts are sodium chloride and potassium chloride, and the particles of this type of salt are non-spherical, and we don't know their effective density. But again, you will need to convert the diameter from one to another into another, but this time to get an homogeneous display of your results. You will understand here, it's really easy. You can display your data, so the fractional collection efficiency as a function of the diameter, with no conversion at all. And so you get the wider particle size range, the widest particle size range, but you mix two diameters on the same graph, so it's not really consistent. But you get particles, data for particles between 26 nanometer and 2.5 microns. If you now choose the electrical mobility diameter, so you converted the aerodynamic diameter into electrical mobility diameter, you still have the information for particles diameter of 26 nanometer, but the largest size for which you can have info or fractional collection efficiency is now 1.7 micrometer for this kind of sodium chloride particles. And now, if you choose the aerodynamic diameter, you will be able to display data for 2.5 micron particles, but your fractional efficiency curve will start only at 52 nanometer. So you can make your data set say very different thing if you don't know the effective density, or depending on the diameter you choose to display your data. Another example of the for this time for N95 respirators. So same types of graph with the fractional collection efficiency as a function of the particle diameter. In red, as a function of the electrical mobility diameter, and in green, as a function of aerodynamic diameter. And as you can see, the less filtered particle size, in one case is 36 nanometers, and in the other case, it's 72 nanometers. And this is important and can be important when you want to choose the right respirators, if you want to evaluate the exposure with the different kind of respirators. Sorry. So again, if you use the same graph, the same image as I presented just before, and you look at the deposited fraction in the alveolar area of the lungs, 36 nanometer will give you 40% of deposited particles. 72 nanometers will give you only 20% of deposited particles. So here again, you see that even in protection and mitigation, effective density is really important. So now, to conclude, firstly, the PNM aerosol exposure should not be assessed only according to mass concentration. Number or surface ones can be more relevant. For number concentration, real-time number particle size distribution measurement can require the effective density, and it's better if we can have the size-dependent effective density. For improving the reliability of the number concentration, for converting number particle size distribution to mass particle size distribution, to have real-time mass PNM distribution for comparison purpose with existing mass TLV for nano or micron-sized chemical compounds. Secondly, the PNM aerosol real-time and finely discretized sizing is often based on electrical mobility diameter. And effective density will be required for converting one diameter into another, or the contrary, for that, also for data analysis purposes. So as I said, to determine the size-dependent deposited fraction in lung areas, to choose the most relevant way to display your data, as I show you in the filtration experiment, and to characterize and select the right protection equipment. And finally, you will also need that to be able to compute, to perform good CFD simulation and modeling of filtration kinetic and aerosol dispersion in workplaces. Last line, and maybe it's the most important thing I want you to remember. The PNM aerosol study in OHS requires fundamentals to very applied works through the three field or aspects I discussed in this talk, but all require a high level of aerosol characterization if you want to have data of quality. It's not easy, and especially in workplaces, it's not always possible, but everything should be done to have the highest level of aerosol characterization in order to have the most precise data. So that's the end. Thank you for your attention. If you have any question.
Merci beaucoup, Loïc. C'était très intéressant. Je ne vois pas de questions en ce moment. Mais perhaps I can ask a question, Loïc. With your conclusion, Does the Rsst, for example, offer this type of services? So if you have an industrial environment, for example, and you're trying to understand level of exposure or what sort of protective equipment you should invest in, where would you go?
We do that in project. Sometimes when we are studying a workplace, at the end we will do recommendation about protection or mitigation protocol, and we can do also expertise. We have, for example, in autopsia or in other kind of workplace, people can ask us to do some measurement, to study something really applied. But for the effective density, for example, it's a research question right now because it's complicated to measure it without a lot of instruments. It can be expensive, and we are still now creating methods to do that in workplace directly. We have, for example, a project on welding fumes where we want to study the influence of the different material of the cores on the effective density.
Okay, thank you very much. I don't see any other questions, so thank you very much, Loïc, for this very interesting talk, and I'll invite you to unshare your screen. And at this point, I'd just like to thank Ludwig for putting this great program together. I also want to thank all of the speakers for their time and for sharing their knowledge with us. And for the audience, of course, who are here today. And we remind you that we have another health and safety webinar coming up in September. So once you are very rested after the holidays, and please check the NanoCanada.com website because you can now register for our October 21st virtual launch event. And this is a virtual launch to our international conference that will take place in person in a year from now, in June 2022. So please join us, register, and we will be with you again, hopefully in September for our next webinar or October for our launch event. So thank you all, and à la prochaine. Merci beaucoup.